Geodesic curves are the shortest connections between 2 points. In the Euclidean plane, a rubber band contracts under the tension of the rubber molecules to a straight line which minimizes length. Geodesics are used in mathematics as a fundamental intrinsic concept in the study of surfaces and general manifolds. To find the shortest curves on Earth, we cannot take the straight line in space, but need to restrict all curves to lie on the sphere. Here, geodesics are segments of great arcs, paths which are taken by airplanes and ships. The boundary value problem for geodesics on general surfaces leads to different local minimizers, which all have minimal length compared with nearby curves. In a different interpretation, geodesics can be considered as the straightest curves on a surface. For example, when emanating a light particle in a certain direction, it will travel along the unique geodesic with the same initial point and direction, a property already noticed by Fermat in the 17th century. The straight line property of geodesics makes them a suitable concept also in numerics and visualization. For example, point waves on surfaces evolve through distant circles. The singularities of the wave front are the conjugate points of the exponential map in geometry. The wavefront develops caustics at the conjugate points with the shape of a swallow's tail. For numerics, it is helpful to define discrete geodesics on polygonal surfaces. Planar faces are like Euclidean planes. The definition across an edge is an intermediate consequence, since both faces are isometric to a planar domain. The geodesic has equal angles at both sides of the edge. The situation at vertices is more delicate and uses the definition of discrete geodesic curvature of a curve. Light rays show a discontinuous behavior at the vertex. The situation can be better studied in a planar model. The light rays away from the vertex are straight lines, and the ray through the vertex bisects the total vertex angle. The definition of discrete curvature of curves allows an intrinsic description of curves similar to smooth surfaces. It uses the discrete Gauss curvature of a vertex. The normal vectors around a vertex enclose a patch on the unit sphere, whose area is the discrete Gauss curvature. A planar domain has zero curvature, and at a hyperbolic vertex, the patch changes orientation and has negative area. The total curvature of a discrete surface is concentrated at the isolated vertices. As a consequence, waves on discrete surfaces have singularities which are equivalent to those at conjugate points on smooth surfaces. Behind every vertex, there are 3 interfering waves, one from the left, one from the right, and a third segment generated at the vertex. The simulation of waves on surfaces and discrete geometries is an example of the use of intrinsic geometric properties in numerical integration of differential equations and the visualization of flows on surfaces.